Hi there. Quick review, and then we're going to get straight into dilations. First of all, parent functions. You got to know what these things are. Parabola, x squared, 0, 0, 1, 1, 2, 4 are kind of some of the key points that you typically see in a table, and then the reflections, negative 1, 1, and negative 2, 4. Over here, we've got our absolute value function, which is 0, 0, 1, 1, 2, 2, and then the reflections, because absolute value means change that value to positive, or the distance from 0. So it's negative 1, 1, and negative 2, 2. So it comes down to a point, this comes down to a curve, and then finally the square root function, basically a half parabola on its side, so we start at 0, 0, don't have it marked there, 1, 1, and then 4, 2, because the square root of 4 is 2, and we're only going to take the positive square root with that particular function. All right, we'll come back to these, but you should know what these are already. A little bit more review. If I can find my notes here. Here they are. Translations and reflections. You should be comfortable with telling someone, not necessarily me, someone, what this all does. So first of all, parent function, we know that's going to be a parabola. But we've also got a negative out front, so that tells us that this is going to be a flip or a reflection across the x-axis. So we know that's going to be the parabola upside down. And then our vertex is going to be a negative 2 because it works kind of counterintuitively inside the function, and a negative 3 on the outside of the function because basically I've just subtracted 3 from y. So negative 2, negative 3 is going to be about right here. And this is going to be upside down. So essentially when I graph this upside down, I'm going to go over 1, 1. And then I'm going to go, essentially, I'm doing this in my head kind of backwards, is 2, 4. So that shape looks like that, more or less, when I'm done, except not curved out quite that far. Oops. Looks more or less like that. That should be more of a curve, but that's the way it looks. And notice the points. The 0, 0, the 1, 1, and the 2, 4 kind of turned on its head. The next one, g of x, absolute value of x minus 4, not a lot there. So first of all, we know it's an absolute value function, so it should be the v. And all we've shifted is the x component, so it's going to be opposite of that. So 1, 2, 3, 4, we don't have anything added out there, so 4, 0 is our vertex. And so that looks essentially like that, where these points would be up 1 over 1, up 1 over 1, back 1 over 1, back 1, up 1, yeah, I guess. Okay, but that looks exactly like our parent function, except moved over. And then finally the last one here, and I did this one special because this one's got a negative on the inside. And the negative on the inside is a flip from left to right, or a flip reflection across the y-axis. For our little shortcut to for that to be the opposite, it has to be written this way. I'm not going to. So I was saying, and my phone went off, so I may be repeating myself. Negative on the inside is a flip from left to right. Needs to be written this way for us to know that this is a positive 2. If it's written differently than these parentheses around here, it may actually be a negative 2, depending on how it's written. But this is the way this is written here, definitely a shift, positive 2 direction, up, down to positive 4. This means it's shifted left, right, and it's still going to look like a square root function. So this is going to look like this. We've shifted over to positive 2 for our endpoints, not technically a vertex, and up 4, 1, 2, 3, 4. So there's my endpoint, and instead of going this way, it's a flip left to right because of that there. And so we're going to go up 1 and back 1, and back 1, 2, 3, 4, roughly right there. So this thing looks roughly like this. Okay? So that's what that is. Okay, new stuff. Once we understand that, if you don't understand that, you need to go back and watch my other video. All right, I can put a multiplier out in front. I can put a multiplier inside the function, although in most cases you're going to see it as a divisor because that helps us think about it easier, what happens with this. And so this has got a combination of both. All right, multiplier. You could probably guess this. Okay? Multiplier is going to stretch it out or dilate it in the y direction. In this case, nothing added on there, so it's my vertex is still 0, 0. Previously, this was 1, 1, but now it's going to be 1, 2, because 2 times that 1 is going to be twice as high. And previously, it was 2, 4. Now it's going to be 2, 3, 4, 5, 6, 7, 8 kind of off the graph, but 2, 4. So this is going to be the same thing, only much steeper, and then I'll have symmetrical points out here. So it'll kind of look like that. Once again, that should be more curved at the bottom, but that's what it's look like. Twice as high as our normal one. So basically, this is a stretch times 2 in the y direction. Over here, now these are all connected, so you can think about them multiple ways, but we're going to think about this as if it's a stretch in the x direction. So when I divide by some number, that number I'm dividing by on the inside of the function is how I'm stretching in the x direction. And once again, you could also think about this as a compression in the y direction, but we're not going to think about it that way. It's much easier if you think about it this way. No, it's going to be, parent function is a v, absolute value. 0, 0 doesn't change because I haven't added or subtracted anything from it. Before that was a 1, 1, but because I'm stretching in the x direction, it's 1, 2, 3, and just up 1. And then if I was going to go another, it'd be another 1, 2, 3, and up another 1. So it looks roughly like that. And then I'm going to have my symmetrical points, which are roughly there and there. So it looks like that. Now you can verify all this stuff that I'm doing in a calculator or with tables. I'm not going through that. I'm just showing you the patterns. You probably should do some of these on a graph with tables to make yourself understand that this definitely works. But in this case, this is a dilation or a stretch times 3 in the x direction. I know that looks like an x and an x, but it's times 3 in the x direction, or times 3 horizontally. Whereas this was on the outside, times 2 vertically. All right, so what if we have both? Well, you're going to get both of these, and this is why this way of thinking about it is pretty powerful. Okay, so I'm going to put this over here. This is not reflected in any way, so it's only going to be going to the kind of left because that's the way that the, sorry, to the right. So 0, 0 is still going to be my endpoint. Previously, the first point was at 1, 1, but now I'm twice as high in the y direction and 3 times as far in the x direction. Okay, so my first point, instead of being at 1, 1, is going to be here, and my second point, which was at 4, 2, if I remember correctly, if we go back and look at my other note, let's go back and look at that. My other note, my second point was 4, 2, so that one, it's going to be twice as high in the y direction, so that's going to go all the way up to 4, and 3 times as wide in the x direction, so that's going to be 12. All right, so I don't know if I can fit it on here or not, so it should be, yeah, it's not going to fit on here, but out 1, 2, 3, 4, 5, 6, 7. Basically, our next point is out here at 12, 4. It's not to scale here. I ran out of room on my paper, but essentially it's going to look like that. So these dilations follow a similar pattern. If they're on the outside, they do it to the y. If they're on the inside as a divisor, they will do that same kind of pattern to the x. I'll leave it to you if you want to figure out other variations of that, but this will work. And then finally, I got a little quiz for you. So your quiz is this. I'm hoping I can make all this fit. So we got a square. It's going to be flipped. It's going to be 3 times as high as the in the y direction, or dilated in the y direction by 3. It's going to be twice as wide in the x direction, and then it's going to be shifted over, up, down by 1, or over, not over, down by 1. All right, so if I was going to do that, so first of all, my new vertex is a -5, -1, so 1, 2, 3, 4, 5, -1, so there's my vertex. I know it's going to be upside down. Typically, I'd be at 1, 1, which would be roughly right there, but that's not my new point. It's going to be 3 times as far from that point, and it's going to be 2 times as wide. So instead of right there, roughly. Okay, so this is a really rough sketch, and I'll have symmetric. But all my points will be, if I was going to look at the original table flipped upside down, it would be all my y's would come out 3 times as high, but twice as wide. I hope that makes sense. That's all. Ciao.